So last time we started to derive the screening of Coulomb interactions in metals by using only quantum mechanics. And in particular, we applied Rayleigh-Schrödinger perturbation theory and consider the two potential terms V and U, where V is the intrinsic electron-electron Coulomb interactions in the original metals, and U is the kind of a small electron density disturbance induced electrostatic potential. Okay? And both U and V are small so that we could perturb this around. The unperturbed H0 Hamiltonian, which is the free electron gas. So up to second order in those small parameters U and V, and we could find out this contribution to the effective U. And in particular, there, say, up to second order, there are two terms that will contribute to this correction of the U effective. And remember, this U effective is the zeroth order U plus the second order corrections V and U and V appearing in two places. So the first contributions at the second order is when V comes first and then U arrive later on the right, and the second term is the reverse order where V appears on the right and U to the left. So let's just repeat what we have left at the end of the last lecture, that we calculated the first term of the second order contributions, which is this this term. When we expand all this operator content, C dagger and C, in moment and space, and this is what it is. Okay? And we could use a diagram to simplify this calculation. Remember, we need to evaluate this expression value of this messy 6 operator. But in order to get the finite contributions, there are only two possibilities remained. Okay? The first possibility is that when Q is the same as Q prime, and P is given by K minus Q prime, where we could consider the process of that electron scattering through this potential U and V in such an order that first there's a incoming electron carrying momentum P come in and hit the scattering center of U of Q, and then the scattered electron carry momentum P plus Q. But in this case where P plus Q is actually P plus Q prime, which is the same as K. And this K is nothing but that K. Of another electron, incoming electron state, scattered by the Coulomb potential V, right? And that electron state come in and get scattered by V of Q, and after scattering, electron state becomes what? K minus Q prime. So this becomes K minus Q prime, which is this. But we assume that K minus Q prime is the same as P, which leads to the circle around those operators. So this P is nothing but the initial electron states, so that the final state is the same as initial state, so that we could simply just connect these two lines and form the loop. And that's precisely this loop is about. Right? So this is called the Feynman diagram, but this is a way to simplify the calculation. We don't have time to really derive these Feynman rules and Feynman diagrams, but we could discuss that in the the other class. But here we simply just use a diagram to simplify the second order perturbation theory, and we try to evaluate this excitation value, and the non-zero contributions arises in these two cases. The first case is this case, and the second case is over here, which we'll discuss in just a moment. Okay, so let's just focus on the first case, where the final state is the same as the incoming states. Okay, so that we could identify these two states as the same states. Okay, that circle around this potential scattering center U of Q, and also the Coulomb potential V of Q. So the bottom two states are nothing but the remaining electron operators carrying momentum K prime. That's the incoming state, and then when it gets scattered by V, it is given by K prime plus Q prime, which is K prime plus Q. Okay, so this is nothing but these two. Okay, so K prime plus Q prime is this. All right. So by forming this C pairs, we are able to simplify this kind of a operator product in the form of a Fermi-Dirac distribution function, remember, or occupation number operator. Remember, this is the goal of our calculation, or second quantized approach, meaning we use and take advantage of this C dagger and C operators, and we try to form a number operator, C dagger C, with the same momentum, so that this number operator, when we take the expression value, becomes the Fermi-Dirac distribution. Remember, the Fermi-Dirac is the goal. To get the Fermi-Dirac, we need to pair up the C dagger and C operators carrying the same momentum. Otherwise, we don't get any contributions. Okay? So that's the power of a second quantization technique. So therefore, we could simplify this kind of a diagram in a simple loop like this, or a ring diagram. Because this loop looks like a ring, a wedding ring. And this is just up to second order and just one of the contributions. Okay? So let's just discuss the second contribution when Q is minus Q prime, and P plus Q is given by K prime. Okay? In that case, you can also use the same argument here and to derive the same ring diagram like this, exactly the same, right? So when we sum up these two cases, there's a factor of 2 here. So we can simply just consider one of them and multiply by 2. So then let's just collect all this C dagger and C, turn over there, and by using these two cases and taking advantage of this C dagger and C carrying the same momentum index, here K minus Q prime the same as P, so that C dagger K minus Q prime CP is given by MP. So which is what? Let's see where it is. C dagger K minus Q prime and CP, which are these two. So we can move all these operators, and so that these two operators, C dagger K minus Q prime and CP, become neighbors. So when they become neighbors, and we have this assumption in the first case, the second case, so that we can identify that K minus Q prime is the same as P. So therefore, the C dagger PCP is given by the number operator MP. All right? So likewise, you can also move around all these C dagger and C operators to form number operators, but the other factor is actually 1 minus MP plus Q. Okay? So remember these two are number operator, occupation number operators. And so here's a homework, and I already derived the half of this factor MP. So now it's your job to derive the remaining factors. Okay. So in particular, this denominator energy difference, the denominator here is actually the eigenvalues of this operator, 1 over epsilon 0 minus h0. If you simply apply this operator onto all these states, intermediate states, you get epsilon p plus q as eigenvalue of h0. Okay, because of this operators, C dagger p plus q, somewhere here. Okay, and then you multiply the remaining factor, which is nothing but this u. Okay, this small perturbation u. Good, and we multiply this by a factor of 2. So that's the first term of the second order contribution. And similarly, we can consider the second term of the second order contribution, where this again the order of v and u got switched, but we could reorder all these operators and in such a way that we still put this u on the right and v to the left. But then the intermediate factors differ slightly from this first term, in the sense that in the first term we got MP, but here we got MP plus Q, and another factor, 1 minus MP plus Q, in the first case now becomes 1 minus P, MP. Okay? In other words, P and P plus Q got interchanged because you reversed the order between V and V term, U term, and therefore there's an interchange between momentum P and P plus Q. So this is also your homework to derive this operator, the occupation number operator, form of the second order contributions. So now you could sum up these two contributions, and by the way, the diagram, the ring diagram for the second term, the second order contributions is exactly the same as the first term, except now you interchange between P and P plus Q, so now P becomes P plus Q, and P plus Q becomes P. That's all. Good. So now you can sum up these two contributions and take care of this, differences between P and P plus Q, in these two terms, and we could get this corrections, second order corrections, and we could expand this, numerator, and we cancel, two of these terms, and we get this simplified result, where the numerator we get occupation number operator MP plus Q minus MP, and energy denominators epsilon P plus Q minus epsilon P, where this epsilon refers to free electron kinetic energy. Of course, we should multiply everything by U, and also there's a VQ here. Good. So, of course, this result is up to second order imperturbation, meaning up to the order of U times V or V times U. But imagine I could just keep expanding this result up to higher order imperturbation, and you could use the same analysis as we have done over there, and effectively with the higher order terms you simply just add one more loop here and another loop and another loop and another loop. Okay, so that we get this indeed a ring diagram. Okay, so this is the ring diagram. So we could include as many rings as possible at higher orders, and we sum up all such a ring contributions. And that's the full contributions under so-called RPA, random phase approximation. So the total U effective is nothing but you sum over all such ring diagrams. So let's quickly finish this calculation. As I mentioned, the total U effective is the sum of all contributions from all orders, and which is given by the first non-perturbed term U, and plus the second order term, which contains one loop or ring, and also the two loops, two ring contributions, and three rings, and so on and so forth, up to infinite number of rings. And you could simply just sum over all these terms and form a geometric series, because you could simply just define this quantity complicated terms inside the bracket. It's just some kind of a bracket, and you could organize all these terms in such a way that you put all this common factor U in front and multiply by everything inside the bracket, which is 1 plus VQ times bracket plus VQ squared bracket squared plus VQ cubic bracket cubic, and so on and so forth, up to the infinite number of orders in VQ and bracket to the power of n. And you can very easily sum of all these terms by using this identity that you learned in high school, meaning you sum over the geometric series where x represents VQ times this bracket. So the result is simply just U times 1 over 1 minus x, right? Okay, so this denominator is called epsilon of Q, which is so-called dielectric function in ordinary metals, which is 1 minus x. So this is nothing but 1 minus x, where x is given by VQ times bracket, right? Okay. Therefore, the remaining job is to evaluate this epsilon of Q. And so let's just put this Q dependence contents back to the U of Q and epsilon Q, and therefore we have this ratio between U of Q and epsilon Q, and which is given by U effective. You can simplify this ratio and get rid of this Q square, and in the numerator and the denominator, and so you get this thing. And we can define this complicated terms encircled by the red as chi 0 of Q, which we'll call this charge susceptibility, but here is just some number or quantity. Okay, depends on Q. But in the Q goes 0 limit, remember we are talking about the long wavelength small momentum transfer limit, where this plasma oscillations occurs. And in that limit, we can show that this chi 0 of Q is nothing but a constant, which depends on density of states at the Fermi level, and this Ks is nothing but this Thomas Fermi screening wave number that we derived previously from the semi-classical approach. But this is the quantum mechanical version of this Thomas Fermi screening wave number, which is given by 6 pi n e squared divided by Fermi energy, and in terms of Rs, this is approximately given by 4.6 divided by Rs. We will finish this, the last piece of the calculation next time, but let me just sketch how we derive such a constant chi 0 in the limit of Q goes 0. This can be done by evaluating this momentum sum, and we could convert this momentum sum to the momentum integral in 3 dimensions, and we can Taylor expand this occupation number difference and also energy difference, especially the numerator. In the limit of Q goes 0, you can simply just Taylor expand this MP plus Q minus MP up to first order in expansion. Therefore, you get this epsilon p plus q minus epsilon p in this expansion multiplied by the derivative. Okay, the derivative of Fermi function with respect to epsilon p. And now you can evaluate this over the entire energy by converting this momentum integral into energy integral. And the conversion rate is actually, they differ by a factor of the density of states. Okay, so that's kind of change of variables from this momentum integral to energy integral can be found in your introduction to solid state 1. Okay, so then we know that this is actually a delta function in the zero temperature limit because the derivative of a Fermi Dirac distribution right at the Fermi level is the minus delta function, right? So this is partial NF, partial epsilon evaluated at epsilon f, which is minus a delta function, epsilon minus epsilon f. So it's minus infinity when energy hits exactly the Fermi level, so that we could easily evaluate this integral because there's a Dirac delta function here, so that this becomes minus the density of states at the Fermi level. So you plug that in, you get this estimation. All right, okay, so time is up for today, and there are just a couple of relations need to be derived next week to finish this screening of a Coulomb interaction. So now you can see how the Coulomb potential U of Q gets screened because the presence of the V. Okay, so the presence of V is screening the Coulomb potential of U, and vice versa, the presence of U is going to screen the potential V. Okay, so next time we will again summarize this kind of a Coulomb screening effect, by this random phase approximation method. I'll see you next week.